Hello everyone, this video is about the optimization technique that is being utilized in machine learning models, and basically we are going to look at the idea of gradient descent optimization. So as an optimization problem we need to have an objective function, so we'll first look at the objective function that is being utilized for machine learning models, which is actually the training loss function. Then next we'll look at the common loss functions for regression problems and those loss functions for classification problems. And lastly we'll see how the gradient descent optimization algorithm works. So let's start from that of the objective function, or what we call the training loss. That's the objective of the optimization algorithm in machine learning models. So let's recall the target function for most of the supervised learning algorithms can be written in the form of y equals f of x plus e. So this target function is actually the true relationship between the inputs or the covariates and the outputs or that's of the outcome variable. And this target function is usually unknown, so we have to estimate this target function using a certain dataset. And the dataset that is going to be used for machine learning models is usually split into two, as a training set and that's of a test set. So the purpose of these train sets and test set are different. The train set is used to train or fit the model of interest, so the objective is to find a model that can best approximate the target function y equals f of x plus e. And the test set is used for measuring how well the fitted model or the trained model performs for a certain unseen dataset or dataset that is not used for training or that is not used for fitting the model of interest. So the objective of the test set is for that of a generalization purpose. But as you know, in the statistical models the entire dataset is used for fitting the model. But when it comes to that of machine learning techniques, instead of considering all the observations in the dataset, we need to split the data into two for these two different purposes. So basically the training error or the in-sample error evaluates how well the trained model, let's say f hat, or the estimated model f hat, approximated the target function f. So it is just, we can say it is the average of all the pointwise training errors. Just the average of all the pointwise training errors. So this training error is just calculated using that of the training set. So this is called an in-sample error. But the error that is going to be obtained from the test set, it is said to be the test error or out of sample error, which measures the performance of the trained model for unseen data or for data set that is not used for training or that is not used for fitting the model. So this training error or in-sample error, which is just the average of the pointwise training errors, is the objective function that the optimization algorithm aims to minimize. And usually this objective function is called a cost function, loss function, or risk function. And this function is going to be minimized subject to the parameters of the model. So usually we write it as J of W, where W consists of all the parameters of the model, including all those biases and all those weights. So J of W or this loss function is just that of the average of the pointwise training errors. So here y I hat is nothing but It is the function of the covariates and the parameters of the model. So this should be minimized subject to the parameters W. So let's consider the loss functions or training error functions for regression problems. So the first type of loss function for regression problem is mean absolute error. The mean absolute error, which is just the average of the absolute errors. But this error function gives equal weights for each and every error. It doesn't discourage large errors. And besides, this loss function is not differentiable at 0. Therefore, this loss function or this mean absolute error loss function is not commonly used as a loss function for those regression problems due to these two disadvantages. But the one that's commonly utilized is called mean squared error, which is just the average of the sum of the square of the deviation of the predicted values from the true values. Now this one penalizes large errors more significantly than small errors. So this error is highly sensitive to outliers because you have this squaring process. So squaring a large number will make very large or extremely large, but squaring a small value will not have that much impact. So this mean squared error penalizes large errors more heavily. So even if this mean square error has this disadvantage, it is the most commonly used loss function in almost all regression problems. But we have also other type of loss function which is called Hooper loss. Now this Hooper loss acts like that of mean square error for small errors, and it will act like that of mean absolute error for those large errors. So it is defined using this formula. Just if the errors are small, let's say below a certain value, let's say delta, then it will act like that of mean squared error. But for large errors, it will consider something like mean absolute error. So usually this Hooper loss may be just the better loss function in the case of having, let's say, an extreme error or an extreme loss value. So this mean squared error and the Hooper loss are the most commonly used loss functions for regression problems, especially in the case of having some outlier or very large loss values or error values. The Hooper loss may be the most appropriate one. So these three are just the most commonly utilized loss functions or loss functions that can be considered for solving regression problems. Now let's consider that of the loss functions for a binary classification problems. Now in the case of binary classification problem, we have a binary outcome value, let's say taking the value 0 and 1, and the predicted outcome value will be again 0 and 1. So the first theoretical loss that may be considered is binary error loss, or what you call 0-1 loss, because the outcome variable is binary, taking the value 0 and 1, then the predicted value is also 0 and 1, so the loss will be either 0 or 1. So this binary error loss is nothing but it is just the average value of the number of incorrect predictions. Average value of the number of incorrect predictions. But this loss function is discrete, or it is not continuous, so it's not differentiable. So in practice, even if it is defined as a loss function, this is not used as a loss function for almost all binary classification problems. Therefore, instead of considering it as a loss function, it may be better to consider this error as a measure of performance of the trained model, Otherwise, it's not good to consider this loss function as a loss function, because it is not continuous and it's not differentiable, so it cannot be used as a loss function due to its difficulty, because this function cannot be minimized with respect to the parameters of interest. So another commonly used loss function is actually the binary cross entropy loss, or which is called log loss. So this binary cross entropy loss or log loss is just a function of the actual value of the outcome variable and log of the probability of success. So unlike that of the binary error, this function is continuous and it is also differentiable. So instead of considering this y I hat, which is the predicted value of the model, which is either 0 or 1, it is better to utilize that of log of the probability of success. Therefore, this loss function is continuous and it is also differentiable. As a result, it is the most commonly used loss function for binary classification problems. And another most commonly used loss function is also called binary cross entropy with logits. So this binary cross entropy with logits is a function of that of the actual value of the target variable and the logit of the probability of success. So again, unlike that of the binary error, which takes the values either 0 or 1, now this binary cross entropy with logits loss function is continuous and it is also differentiable. And compared to that of the binary cross entropy loss or log loss, this binary cross entropy with logits is assumed to be the most stable loss function. So this is just the most stable loss function compared to this binary cross entropy loss or log loss. Therefore, in general, this binary cross entropy loss and binary cross entropy with logits are the most commonly utilized loss functions for classification problems. Now let's consider the idea behind gradient descent optimization. So as we have seen before, most of the machine learning models have loss functions. That's the objective function that is going to be considered as objective function, and that's the optimization algorithm aims to minimize. And this loss function is actually a function of the parameters of interest. But most of the time, this loss function is impossible, or it is difficult to find the minimum analytically. Rather, we have to consider a numerical method called gradient descent algorithm. So the idea of this gradient descent algorithm is just moving the parameter value little by little in the direction that the loss function decreases. This is just the idea. Taking at a certain arbitrary value for the parameter of interest, we are interested or we are required to move that parameter value little by little in the direction that the loss function decreases. So let's consider, suppose we have a certain model having only a single parameter. Let that single parameter be W. So the idea is to start with a certain initial parameter value. Let's say W naught at time is equal to 0. Something like W naught at time is equals to here. Then we need to get the first derivative of the loss function. Let's consider J prime, which is the derivative of the loss function with respect to that parameter. Then we need to obtain the new value of the parameter or the updated value of the parameter using this formula. The updated value of the parameter equals the value of the parameter minus lambda times the derivative of the loss function. So here lambda is greater than 0 and it's called a step size or learning rate, and we'll come to this point in a moment. So here the updates will decrease the value of the parameter if the derivative is greater than 0, and it will increase the value of the parameter if the derivative is negative, or if it is less than 0. So updating the value of the parameter using this formula continues until the parameter value converges, or until no further improvement in the value of the parameter is obtained. So initially the value of the parameter may be something around here, the loss function value is here, then the next update it may be here, then the value of the parameter may come here, and the next update it may be around here, the loss function, and the value of the parameter will be around here, and so on. So the update continues until convergence. We need to find the value of w around here, which minimizes the loss function. So in this graph, that means the derivative of the parameter is something like greater than no, the derivative of the loss function is negative. So in each update we are increasing the value of the parameter. So we have here this parameter lambda, which is called learning rate or step size. So it is just a step size hyperparameter or value that should be specified, and it controls how much to move at each time in updating the value of the parameter. So in general, if the learning rate is too small, then it may take a large number of iterations to reach to the optimal value. But if we take a large learning rate value, in that case, the algorithm will never converge. Rather, it will oscillate back and forth without convergence. So in the case of small learning rate, the algorithm will converge, but the number of iterations required to reach at the optimal value will be too large. But in the case of a large learning rate, the algorithm will never converge. Rather, it will oscillate back and forth due to the larger the learning rate. So the optimal value around here will never be obtained. And we have another type of learning rate called dynamic learning rate. In this case, it is better to take large steps or large values of the learning rate initially, and later on it is better to decrease the value of the learning rate as we approach to the optimal. So in this case it is called dynamic learning rate, because we are considering large learning rate values in the initial iterations, but in the final iterations we are taking smaller learning rate values. So considering a dynamic learning rate is usually the better approach. So for example, let's consider, suppose a loss function for a certain model is given something like w to the power of 4. Let this be the loss function of a particular model. So first we need to obtain the first derivative, that's 4 w to the power of 3, and let's initialize the parameter as 2, and let's consider a learning rate of 0.01. So at time step 0, the value of the weight parameter is 2, which is initialized, something like here 2. Then next, at time step 1, w1 equals w naught, the value of the parameter in the previous time step, minus the learning rate 0.01 times the derivative of the loss function evaluated at the previous value of the parameter w naught, that is 2.0. So it becomes 1.68. So in the next iteration, the value will be somewhat less than 2. At time step is equals to 2, the value of the parameter w2 equals w1 minus 0.01 times j prime of w1, the value of the loss function evaluated at w1, that is at 1.68. Then it becomes 1.49. So again, the value of the parameter is being decreased. So the update continues until convergence, or until further improvement is not possible. In fact, following this procedure, it may take a large number of iterations to reach to the optimal value, that is 0. But the idea behind this gradient descent algorithm is this one. Just we initialize as a certain value and then we update the value of the parameter value in the direction that the loss function decreases. So there are different types of gradient descent algorithms. One, it is called batch gradient descent. In this case, the gradient is computed using the entire training dataset. But when you have a large number of observations in the training dataset, so computing this batch gradient descent will be computationally intensive. So we have another way, which is called stochastic gradient descent. Now this one uses one training example at a time for computing that of the gradient. And possibly there is also another method called mini batch gradient descent. In this case, the gradient is going to be computed for a batch of training examples. Let's say 16 training examples, 32 training examples, 64 training examples, and so on. Usually a batch is going to be considered a value which is just something like to the power of let's say 3 to the power of 4 to the power of 5 and so on. So these are the three types of gradient descent algorithms, considering the entire dataset to compute the gradient, which is called batch gradient descent, considering one training example to compute the gradient, which is called stochastic gradient descent, and considering a batch of training examples, which is called mini batch gradient descent. But these gradient descents have some limitations. One, it requires the loss function to be convex. There should be just one local minimum, which is a global minimum. Otherwise, if we have several local minimum values, in that case, the gradient descent algorithm may stack on a certain local minimum. And there is also another problem which is called gradient vanishing problem. If the derivative of the loss function is 0, then the value of the parameter will not be updated. Let me go back to the definition of the update rule here. If this gradient is 0, then Wt plus 1 and Wt will be the same. That means the value of the parameters are not being updated. So this is called gradient vanishing problem. Gradient vanishing problem. Therefore, gradient descent have these two major limitations. So to avoid these limitations, there are some improvements made in order to smartly control the learning rate and in order to escape certain saddle points or local minimum values. There are other improvements which is called momentum, and there is also another optimizer called adaptive moment optimizer, or which is called ADAM. And there are also other improved versions of gradient descent. So this is all about just the idea behind the optimization algorithm in machine learning algorithms, using that of the gradient descent optimization technique.